The first engineering challenge of any automation project is transforming raw, unconfigured physical hardware, like a C6017 IPC and its attached EtherCAT terminals, into a precise, real-time control application. The TwinCAT environment serves as the software bridge, connecting the physical constraints of industrial hardware directly to real-time executable logic. The scope of TwinCAT is extensive. It handles everything from managing multi-PLC systems to NC axis control, down to direct input and output manipulation. To utilize these capabilities, a control systems developer must first complete the essential task of linking physical EtherCAT field bus nodes with virtual PLC variables. Mastering TwinCAT commissioning is a matter of mastering this translation pipeline, taking physical states and turning them into addressable digital logic. The TwinCAT architecture enforces an absolute rule: strict operating state separation. Config mode is the exclusive, required state for hardware discovery, system mapping, and making any structural modifications to the environment. Conversely, run mode is reserved strictly for real-time execution, compilation, and live operation. When a system is in run mode, the structural configurations are locked. The interface used to manage these operating states has evolved across generations of the software. TwinCAT 2 splits the workflow into two dedicated applications. The system manager handles the electromechanical hardware mapping, while PLC control serves as the environment for the software code. This image displays the Visual Studio 2010 start page. TwinCAT 3 abandons the bifurcated approach, unifying both the hardware and code workflows entirely within the Microsoft Visual Studio shell. While the UI is now a single shell, the underlying pipeline logic remains identical. We can trace the definitive setup workflow across both platforms. The first phase in the commissioning pipeline, regardless of software version, is targeting. The environment must identify and connect to the specific physical machine it needs to address. Here, in the General tab of the legacy TwinCAT 2 System Manager, the user initiates local versus remote targeting via the Choose Target button. In the modern TwinCAT 3 environment, the identical targeting process opens this Choose Target System dialog box, utilizing the Search Ethernet function. This Add Route window shows how an engineer inputs destination data to establish remote connection routing. The engineer can manually enter a known host name, IP address, or AMSNet ID. Alternatively, performing a broadcast search will ping unknown Beckhoff devices on the local network. Successfully locking onto a target transitions the setup from a localized software instance to an active connection with the physical machine, enabling device discovery. With the machine targeted, the workflow transitions into config mode to initiate hardware discovery. The system must query the physical bus. This image illustrates the physical scanning workflow in the TwinCAT 2 System Manager, navigating directly underneath the I/O devices tree to execute scan boxes. The TwinCAT 3 scanning procedure operates identically, utilizing a simple scan command within the unified left-hand project folder explorer. Acknowledging the resulting Find New Boxes dialog populates the I/O tree, assigning the detected terminals into the software's logical structure. Following the scan, the system prompts the user to enable free run mode. Enabling free run allows the programmer to directly manipulate terminal input and output values while still restricted to config mode. This serves as an essential diagnostic tool for purely physical hardware verification. The scanning phase translates dumb physical hardware on the factory floor into a structured, addressable digital database inside the TwinCAT environment. Phase 3 is logic integration. The hardware is mapped, but it currently lacks any programmed instructions to execute. Returning to the UI split in TwinCAT 2, the raw code written in PLC control operates completely isolated from the hardware tree mapped in the System Manager. To bridge this gap, the saved PLC project file must be explicitly imported and appended directly into the System Manager's configuration tree. This variable configuration interface highlights the final allocation step, where the user actively links a specific terminal channel to a Boolean variable via the Change Link context menu. The underlying data architecture maps process data objects, or PDOs, from physical terminals to specific variables flagged with the @identifier in the structure text. This allocation requires an exact data type match between the code and the terminal. A Boolean must map to a Boolean for the link to hold. Variable allocation is the precise moment the software logic and the physical machine fuse together into a single system. Once all variables are linked, the environment initiates the activation protocol. The software must check the configuration for errors before it can be activated. During activation, the settings built in the System Manager are compiled and forcefully transferred into the real-time runtime system. The engineer must confirm mandatory system prompts, acknowledging that old configurations will be overwritten and the TwinCAT system will restart into run mode. The programmer formally logs into the PLC environment and executes the run command. This display of the TwinCAT PLC control window shows definitive proof of a successful setup. The blue data boxes in line with the code reflect real-time Boolean and hex values actively updating. Observing live data reading back from the hardware confirms the commissioning pipeline is complete. The digital logic is actively driving physical reality. Returning to the modern standard, TwinCAT 3 executes this multi-step pipeline: target, scan, link, activate, run. Structurally, TwinCAT 3 embeds this entire complex, multi-application process into a single unified project file format. This TwinCAT 3 New Project dialog box highlights the TwinCAT XAE project selection. The software architect builds the entire pipeline from this single starting point. Visual Studio integration eliminates the disjointed, repetitive toggling between separate configuration and logic applications required by older platforms. Despite the streamlined interface, the core sequential dependencies required to safely spin up a machine cannot be bypassed. Software shells will continue to evolve, but the core engineering discipline of bridging hardware discovery with software allocation remains the foundation of industrial automation.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.